Okay. Well, thank you for allowing me to talk about this topic here. I was really pleased to see that resilience is one of the major themes of this particular meeting. It's an area that I've been particularly interested in over many years. Much of it's been going on outside this lab. And originally I thought this talk would be about a fairly detailed technical talk on our use of probabilistic modeling and analysis for strategy synthesis, and I had intended that my colleague would give the talk. He is stranded in Europe, and actually I had to fly in last night. So I'm going to give a somewhat broader overview with pointers to the more detailed work, and probably could talk more about it offline. But the idea here is to give some sense about, more broadly, how we're using formal modeling to reason about adaptation. So I'm sure I'm speaking to the choir here, but the goal here is to improve resilience of systems, where we want systems to maintain operational capability and indeed optimal capability if we can, even in the presence of lots of perturbances. Environments will change. There will be faults in the system that you simply can't predict in advance. There will be attacks and other kinds of security issues. And there may even be changes in user needs and the context in which the system is operating. Today's current resiliency improving mechanisms tend to be fairly brittle, costly, and hard to verify. So what are those mechanisms? Well, traditionally, you would embed a lot of low-level code that deals with resiliency, where you wire into your implementation various policies and various strategies for fixing things. Might use things like timeouts, might use things like exceptions, and so on. The problem with that is it tends to be fairly low-level. It has a very local view of the problem. And it's very difficult to modify later because it tends to get dispersed throughout the system. The other alternative that we see a lot are you have humans. You have operators who are standing there who are observing the system. They have the opposite problem, that they tend to have a global view, but they tend to also be slow. They make a lot of mistakes, and they're very costly to keep as part of your system. So the goal here ultimately is to make systems much more self-sufficient, self-adaptive, self-repairing, self-securing, and so on, so that they can respond automatically to the things that occur at runtime, including some of the problems I mentioned earlier, but in the security world, being able to respond to various kinds of attacks. The question is, how do you do that? And so I think as a general point of view here, philosophy, if you will, we need to think about moving from open-loop systems to closed-loop systems in which we have a layer of system structure that is responsible for monitoring the system and affecting it or changing it based on the observations of its current behavior. So the question is, well, what does that control level look like? And so that's been the focus of a lot of research that we've been doing, where we've primarily looked at model-based adaptation, where the goal here ultimately is to provide accurate models of the system that permit reasoning about both whether there are problems and, second, what you should do about them. Now, this isn't new, and in fact, if you look around at industrial systems of all sorts, you'll find that people do that already. This is an old depiction of a Google file system, but sort of central to their whole resilience practice is a component called the GFS master, Google File System Master, that's responsible for detecting when servers go down and responding by taking whatever information was stored on their disks and spreading it out across the remaining resources. Of course, that's a very specific, somewhat ad hoc solution tailored to their individual needs, and somewhat focused on, or very focused on, a particular kind of fault in the system. So if you look around, you'll find that these mechanisms all around. To the extent that this component has a kind of a global view of where all the data is, what the various replications are, which servers are running, and so on, it acts as a kind of a model-based controller here that can, at runtime, decide what to do. So it's an example, a very specific example, of the paradigm that we're talking about here. But, of course, you could have many ad hoc solutions for this. Can you have a sort of more foundational approach to this in which you understand what are the various kinds of moving parts, if you will, a sort of reference framework that would allow you to fairly rapidly deploy these kind of adaptive capabilities in new systems, legacy systems, in a very cost-effective way, where you could make sure that the adaptation was tailored to your particular domain, which might be an application domain, but it might be your business context. And to do that, we would need to be able to consider multiple quality dimensions where you can balance not only security, but performance, for example, privacy, and so on. So the decision-making that has to go on to decide what to do is going to have to be sensitive to that context where that has many sorts of dimensions that might be relevant. Where we can fairly easily change the adaptation rules, augment our adaptation capabilities over time, and be able to ultimately reason about that, to what extent, what kinds of envelopes of behavior can we respond to, what's outside the domain of things that we can actually deal with, and what are our assumptions, and so on. So I want to focus mostly today on this assurance issue. How do you actually reason about your adaptation mechanisms? So to experiment with this, we've developed a framework that we call Rainbow. This is about almost a decade old now, but we've been playing around with it, augmenting it for some time. And the idea is to follow that sort of general closed-loop control pattern that I showed earlier, but in particular to investigate the use of architecture models for reasoning about adaptation. So when you have a system, often the information you're getting out of it is fairly low level. Trying to understand from that what's actually going on in the system at a systems level and reasoning systematically about the overall system qualities requires a level of abstraction in your models. So what are those abstract models? Well, you can imagine a lot of them, but we're looking at how do you abstract what the system is doing into an architecture model that represents at a high enough level what's going on in the system so you can decide what to do. Secondly, we want to be able to tailor this to specific domains, which means we need various extension points that are going to allow us to say, in this domain, these are the kind of problems we're looking for as compared to some other one. And from an engineering point of view, separate the instantiation of the paradigm into a set of pluggable points or extension points that include things like what kinds of sensors you have, what sort of actuation interface you have to the system, what kinds of architecture models you're using, what sort of conditions are relevant for adaptation, and importantly, what kind of repair policies you have. So that's a framework, meaning something that actually runs, that you can actually use, you can instantiate, you can build systems with that. But core to that is a way of actually specifying the adaptations that you want to do. In the end, our goal is to be able to reason about those adaptations and the extent to which they meet our goals. And so for that, you need some way to be able to express those that you could, in principle, feed to automated tools to give you some insight into those. So at a very abstract level, what we have is a system here. We have this adaptation layer. Within the system, we have a target system. We're going to be monitoring it translating the lower level observations about the system to higher level observations that can update models in a model manager, and then have an adaptation manager that's looking at these models at runtime and actively trying to improve the system. At a more detailed level, this is what Rainbow looks like. There are a number of moving parts, and each of those can be viewed as a kind of a plug-in that gives you tailorability of that. So you can plug in what kinds of architecture models you want, what sort of properties you're monitoring, what kinds of problems you're looking for, you're trying to detect, what sort of actuation interface you have to the system, and so on. So all of these become parts of the system that can be tailored. So just to give you a very simple example, imagine that you're working in a context of an n-tiered system where you have clients and servers, some sort of load balancer, and in this case, you may want to preserve certain kinds of quality of service guarantees. So this isn't specifically a security scenario, but it could be extended, and we have for things like denial of service. And in that scenario, what you have are a set of possible actions that you can do. You can add new servers, you can change the fidelity of existing servers, you can reboot servers and things like that. There's some kinds of condition that you hope to achieve, in this case, maintaining some kind of performance threshold here. And on top of that, you're going to build this extra layer that's going to try to maintain that condition, and using those actions as points of leverage on the system. So what does that look like? Well, in the model manager, there's a representation of the system as it's currently running. This gets annotated with various sorts of properties that represent loads, response times, and so on, that are derived from fairly low-level network monitoring. Those are then updated as the properties of that model. The architecture evaluator is looking to make sure that certain kinds of constraints are satisfied. And when problems are detected, we can do various actions on the system that are then translated into lower-level scripts and other actions that can actually change the system. But the critical question that I want to talk about today and focus on is, well, what goes in here? What's in the adaptation manager? How does it know what to do? How does it decide? What are the right kinds of repair strategies to execute? And can we provide some kinds of formal guarantees about that sort of behavior? So when we consider what needs to happen in terms of selecting appropriate actions, the first problem is, well, how do you quantify what's appropriate? Given that you're working in a multidimensional space of qualities that might include things like performance, content quality, user distraction, security issues, and so on, and that those will vary from context to context. So our approach is to use a utility-based form of evaluation in which we have a set of dimensions. We can talk about sort of utility curves within those. We can talk about weights of the various dimensions, and we can come up with a formulation, basically a numerical score for the quality of the system at any given state based on the utility that it's providing to our business and to customers. We've also experimented with other more general forms of utility, but I won't go into those now. On top of that, we have some notion of tactics, which are to some extent the primitive operations that you can perform on the system, actually implemented by more complex operations in the system. But at the abstract level, we want to think about this as our vocabulary of repair actions. So in the context of ZNN example here, we might be able to switch the servers to text mode instead of full multimedia mode, We might be able to add new servers, remove them, and once we have a set of tactics, then we can consider how do we put them together into larger strategies that will use various tactics in combination, typically, to achieve the goals. So we have a tactic repertoire, we have a set of strategies that we can specify or derive, and then we want to be able to select the right one at runtime. Yeah?
So a quick question about your utility and weight thing. So basically you have a bunch of dimension-specific, piecewise constant functions in this example, and you're just weighting them independently?
In the simple form of this, yes.
Okay.
Yes.
And do you have like any restrictions on the type of utility classes you consider? Do you have like convex?
No.
Okay.
No.
Just general.
No. There are, of course, lots of other formulations for utility. So, for example, one of them that we're looking at now separates out risk as a separate dimension. You know, what is my risk profile? So that's a whole separate area, but somewhat independent of what I'm talking about here, assuming that you have some way of evaluating the states with respect to your business goals. Okay, so associated with the various tactics, at least in our initial version of this, we had a fairly simplistic notion of impact, which is how does it actually affect the utility across various dimensions. Today we have a much more nuanced notion of impact that actually talks about how the state of the system is changing. So I'm not going to go into a lot of details here, but simply to say that over about a decade we've done lots and lots of experiments with this in a variety of contexts, and the results are encouraging in that the systems do seem to be able to respond fairly well to disturbances, and there are a bunch of papers on that. More recently, we've been looking at security applications, and in particular, how do you deal with things like situations in which some of your clients may be malicious, and part of your modeling effort is to try to quantify or bound that maliciousness within your system reasoning. So I'll say a little more about that later. Okay, so I want to come now down to, well, how do you decide what strategy to use, given that you might have a set of them, or how do you come up with a strategy, or given a strategy, how do you understand what its range of appropriate contexts for using it are? So to do this, you need some kind of formal way of processing these strategies, of reasoning about what will happen there. So the basis for that, for us, was a design of a language that we felt could actually take into account what we felt were necessary aspects of thinking about adaptation. The first is timing. You might try to ignore that in the first instance of it, but things take time. When you reboot a server, you have to wait a few minutes before it actually happens. Other kinds of actions are instantaneous, so I can flip a server to serve only text as opposed to multimedia content, and that's virtually instantaneous. But reasoning about those kinds of situations or issues or properties are critical here. Utility, I mentioned that, but another aspect of this is uncertainty. Typically, when we're reasoning about what to do, we're working in an uncertain environment. We may not know exactly what's going on outside. We may not even know what's going on inside because our observations of the system are incomplete. The effects of our tactics may be somewhat uncertain also, and so on. So there's a lot of uncertainty inherent in this, and without sort of bringing that into the mix here, we can't make good rational decisions. There may be some strategy, for example, that will achieve a basic result without a lot of uncertainty, or this doesn't depend on, and other ones that are much more sensitive to that, and being able to reason about uncertainty as a first-class aspect of this is, in our view, fairly critical. So the language that we developed for expressing strategies attempts to incorporate these concepts. It's called Stitch, and essentially it represents a strategy as a kind of a decision tree in which at each point you have to decide what tactic to execute. That decision is based on observation of the system as it now stands. So you may start in a particular situation, you execute a tactic. After a certain delay, you're going to be able to see what the result of that is and the environment, and make that as the basis for your next decision, and so on. Uncertainty is represented directly in the model here in terms of the various kinds of outcomes that you might have. And we also include a notion of timing in there about the kinds of delays that we expect to see in terms of executing the tactics. And then finally, as I mentioned, there's a value system associated with this that allows us to say, in this probabilistic world, what's, for example, the expected utility of executing this strategy.
On the last one there, the utility, for a given tactic, do you represent its positive and negative utilities on all of the different utility criteria that you have?
We have different ways of representing it. One is to represent directly the kind of utility delta that the tactic will do, which is a fairly abstract version of it. The other is to try to represent more accurately what we think will be the change in state of the system and then derive the utility from that. So we move more to the second one because it's a much more high fidelity way to reason about it. Mm-hmm.
How do you compute that value function right now?
Which?
You say you're using a sense of moving to a state that may be more beneficial, right?
Right.
It's sort of, this model sort of is a value function-based model where states have values and sort of depend on your tactics interaction with the remaining dynamics, right?
Right.
So how do you calculate this right now?
So I'm getting to that.
Okay.
That's where we bring in the probabilistic modeling tools.
Okay.
Mm-hmm. To tease out the impact of a response versus changes in usage or other changes within the system?
Right. So I've oversimplified things when I showed you that architecture model. In fact, we also have environment models that are independent of that we're representing separately. And we'll see in a minute that as we reason about that in this probabilistic game setting, we'll represent the environment as first-class, uncertain kind of process that can get combined with it. I don't know if that answered your question. Yeah, okay. Okay, so I'm not going to go into the details of it, but basically what we can do is we can propagate up from the leaves up to the root what the aggregate utility is in this very simplistic setting. But I'm going to go into more sophisticated ways to do that. Okay, so Stitch gives you a way to specify these repair strategies, but we'd really like to be able to analyze those in some formal way, for example, to predict the outcomes of the strategy under various environment conditions, say worst case and best case. Worst case obviously being of interest in the security world where you have a malicious environment. The ability to understand for a given strategy what really are the conditions under which it makes sense to invoke that. The ability to quantify the value of adding some new tactics to the system. You may discover there's a region of the state space that you're not very good at repairing, and you can ask, well, if we actually had this other hook into the system, how much better could we do? Ultimately, the ability to synthesize strategies. When we started out, Stitch was mainly invented as a way to offload the knowledge of operators into some form that we could actually execute. But increasingly, we're interested in better coverage of the space by synthesizing those strategies directly from formal models. And then finally, another important aspect of this is how do you bring humans into the loop here? We would love to have everything automated, but in practice, there are situations where you really want to involve the human, either because there's too much uncertainty in the system, there may be situations you haven't seen before, there may be inherent actions that humans can do that the system can't. And so how do you actually bring that into your reasoning about the strategies you want to execute? So those are some goals here that kind of frame a set of research questions that we've been exploring in different ways. So I want to give you some examples of how we're working on those. So the basis for most of the work we've been doing over the last few years has been trying to take these system and stitch models, put it into a probabilistic model checking context by representing the kinds of uncertainty as Markov decision processes, and then looking to be able to reason in that space about optimal policies for achieving some goal. So we've been using the PRISM modeling frameworks underneath, but one of the nice things about that tool set is that in addition to sort of more classical probabilistic modeling, they also have a form of stochastic multiplayer games. And this allows you to think about how do you set up the system and environment so that you can represent things like adversarial or friendly kinds of collaboration among the various parts of the system. So these multiplayer game representations are particularly nice because you can play them through in various ways. Not only can you ask what kind of what is the maximum sort of reward that I can achieve through a strategy, but you can also, by allowing the system to make decisions, or sort of essentially to resolve non-determinism, you can ask the system to generate the best strategy for a given player. So these are fairly powerful techniques, and we've been trying to explore how do we apply that in different ways in this other context. Mm-hmm.
Is the line of finding the equilibrium, or is it just sort of following best response?
No, this is not so much about equilibrium at all. It's more about what's the reward that you can get by executing a certain strategy in the context of other players.
Is that, what is that if not an equilibrium?
Well,
like what is the solution?
Yeah, maybe it could be cast that way. Let me think about that.
Okay.
Let me think about that.
Are the games finite, or are they...
The games are finite.
Yeah, it's a finite game.
Thank you. Okay, so what does this look like? Well, basically, you have to define various sorts of probabilistic models for your system and your environment. You have to define a reward structure on top of that. And then you have to define the properties that you're interested in and feed that into the probabilistic model checker. And you can get quantitative results, such as what's the maximum aggregate utility I can get in this game. Or you could say, as I mentioned before, derive the best strategy that you can for me, given the strategies of the other players. So, as I said, originally I thought the talk would be mostly about the details of this, but I'm going to gloss over some of the specific details and talk more about the applications of it to the work we've been doing. Okay, let's see. So, I think I'm going to skip over that. Right, so we can play out the various sorts of scenarios with these sort of particular kinds of systems. One of the interesting areas that we've been working in recently is trying to understand the importance of reasoning about latency in our strategies. It's very easy in a much simpler models when you don't worry about that. So the question is, how much value do you get by concerning yourself with the latency of things? And so particularly if you want to do this at runtime, the complexity of doing the reasoning can get very high when you have latency in terms of latency as part of the calculation. So we've been doing a lot of offline analysis using these games to say what's the value with and without latency awareness, and at what point does it become really important to reason about the latency. These come out as various kinds of tables that give us some insight into that. We can also look at what's the effect in terms of strategy generation if we add some new tactic. Does it actually improve our repertoire significantly or not? So let me mention another application here. As I said earlier, I think one of the things that people need to really own up to here is that you can't automate everything, and at some point you need to think about how humans fit into this picture here. So it's great to think about eliminating them, but you can't. There are some actions really that humans can best perform or can only perform because they're actually physical actions. But humans may also have a better understanding of context and certain kinds of decisions than the system. So if we think about the broader picture here, if we have this loop of various sensing, decision-making, actuation, you can imagine that humans actually provide capabilities in different kinds of ways. They can work as sensors, for example, giving you more information that you can't observe directly, giving some insight into the model as to whether this represents an anomalous or problematic situation, telling you what decisions to make if, for example, there's a lot of uncertainty or risk associated with the automated decisions you might otherwise make, or actually affecting changes, carrying out some action on behalf of the system directly. So each of those requires a slightly different way of how you might integrate the human. Our initial work has been mainly focusing on this corner here of thinking about humans as actuators. And the question is, when do you ask a human to perform some action on the system as compared to doing it more automatically? Of course, humans introduce an element of uncertainty, both in timing and in quality, that you have to find a way to bound in the system. And there are a lot of possible ways to do that. We actually learned something from Sanders here in terms of trying to apply fairly simple models, at least as a starting point, that capture humans' opportunity, willingness, and capability as a form of a model that says, if there's a human in the loop here, are they in a position to actually help out? Do they have the skill set that would allow them to do that? And more dynamically, are they in a frame of mind to actually do that for us? For example, if they're preoccupied with something else, there's less likelihood that they will actually do it or do it effectively. So I'm not going to, again, go into the details on that, but essentially we can define strategies that involve, or we can define tactics that we say these tactics are the things that humans can do, and then we can define strategies that may involve humans as the tactic executors. And in this case, we were looking at denial service kinds of problems here, where we had tactics that could be automated, like adding capacity to the system, or reducing service in terms of the fidelity of the content. But there were certain decisions that we wanted to leave up to the user, or actions, that is, in terms of things like blackholing clients or throttling the rate at which certain clients can use the system. And those end up in this sort of simple case of two strategies. One is outgun and absorb, which is we throw extra resources at the system to overcome a denial of service situation. The other one is we eliminate the problem through using the user to make sure that it gets done right, which would combine things like blackholing and throttling. Yes?
Why do you think the human is the best to do that? I mean, the black hole and nothing. Seems to me this is pretty much automated actions.
Well, you could argue about a given tactic whether it should be automated or human. So this is more an experiment to say, not specifically on that one, but given that the humans could make certain decisions about how to black hole and who to black hole, because they may have more contextual information. For example, if you observe someone that's abusing their SLA, is that a bad thing or not? It may be there's sort of other business knowledge about that client that would say, no, don't do it. But I think it's less important the specifics of whether those tactics should be done by humans rather than the more general experiment here, which says there are some things that we really do want humans to do.
So this is like a hybrid, where human and...
Exactly. So certain strategies, in this case the outgun absorb, can be done completely automatically. And when we eliminate malicious users, we're going to bring the human into the loop on that. That's the experiment here.
For these tactics that involve humans, do you model the time delay that it would take for a human to do it?
Yes.
Account for that in your decision?
Yes, right. So as with all of our tactics, there's a delay. So to some extent, from the system point of view, there's no difference about that. There's more uncertainty typically involved, and determining in a given moment what's the likelihood of success of that tactic will depend on both sort of external things like their level of training, but also internal things like their level of attention. So it's a little different in that sense.
David, just a quick question on the strategy side. Is the strategy about achieving a particular state, or is it those seem to be more about a particular outcome with some engagement? Is there a higher level definition of strategy that is represented or is able to be represented through this?
Well, the strategies here are mechanisms to improve the utility of the system. Okay, and so we're going to try to understand as I'll show you in a second, under what conditions are each of those strategies most appropriate. So what we want to know is when should the automated mechanisms kick in, and when should we involve humans. And we'd like to be able to reason about that in a fairly quantitative way, so that we can say, if this is the context, this is what you should do. Now, that depends a lot on your business context. So if your business context is, we need to provide service at all costs, even if we're giving it to bad people, then you're going to end up favoring one. And I'll show you how that works in a minute. If you're much more conservative about it, then you end up favoring the other one. So the context is going to be very important here. But that's what we want to reason formally about. And to be able to say, under these business policies, then this is the right time to invoke this strategy. This is the right time to invoke that one.
So the business policies aren't built into the strategies.
The business policies,
no,
they're built into the reward function or utilities that are associated with the outcomes there. So in one context, for example, if we don't eliminate any of the bad people but continue to give good performance, that might be a high utility in that context. Another one that says we really need to get the bad guys out of here, even if we're sacrificing performance for some of the maybe potentially legitimate clients, and that will lead to a very different outcome. Okay, I'll show you more of that in just a second. Okay, so I'm going to skip over that. But the basic idea here is that in our decision tree, certain of the tactics that get executed are human tactics. Okay, and then we can reason about them in the same way, provided we specify, timing, uncertainty, and outcomes for that. Okay, again, I'm not going to go into details about that and how we actually encode it. But the net result is that if we run this in various contexts, we can begin to develop a profile of under what conditions the various choices should be made. So if we vary the capability elements of the user, so the levels of training, and put that in a graph with respect to the numbers of malicious clients, we can actually look at sort of thresholds for when it makes sense to use the user and or when not to. So this is in a context where, let's see. Right. Okay. So this is on this graph. We're looking at the outgun strategy and how that varies with respect to numbers of malicious clients and the training level. The other one we're looking at, if we're looking at the eliminate one, what kinds of accrued utility we get. So we can kind of profile these strategies based on varying the different dimensions. In this case, looking at the training level of the user and comparing that against the various situations which they might have to interact.
So is this saying that for outcome, since it's automated, it's completely independent of the training level of the user? So it's flat across the training level dimension?
Yeah.
What, do you have any idea what sort of fraction of malicious clients might be the kind you would see? I mean, that's an incredibly wide range you studied.
Yeah, sure.
I wondered if it's sort of in very small percents, and that's what I should think about, or?
So you're asking about reality here. It's a good question. I don't think I have a good answer to that. And so on. So the point here is that, again, without looking into the details too much, that we can start looking at these different strategies and the context in which they should be deployed in terms of the kind of utility that they're providing. Okay, let me just mention with pointers to some of the other work here, the kinds of things that we've been doing. So if you're interested, we could follow up. Either you can read the paper or I can tell you more about it. One of the questions is, how do you do efficient latency-aware and proactive adaptation? So for that, we're using actually a combination of probabilistic modeling and also stochastic dynamic programming algorithms at runtime. So the general area of security and using this, I talked a little bit about denial of service, but we're also looking to some extent at moving target defenses. So the extent to which you can use various kinds of obfuscation and redundancy to mitigate these. So those become tactics where I am allowed dynamically to add and remove various kinds of moving target defenses. Human in the loop, I talked a little bit about that. So those are things that we've actually worked on, we've published papers on. Some of the things that we're working on now, one of them is how do you resolve uncertainty, given that you're working in this uncertain world. If the risk that uncertainty causes is too high, you may decide instead of doing something, I should really get more information. And that there's a cost to that, so that becomes a new kind of tactic, cost and benefit, new kind of tactic to actually actively add a new probe or get some specific information about the system. So how do you reason about when it's effective to do that? We're also looking at how can we take the models that we may have generated offline based on our best knowledge of it, but refine those incrementally over time while the system is running, so that as we see what happens when we actually execute our tactics or observe the environment, we can start improving our models incrementally. And then ways to speed up the runtime process here of making decisions about what to do through some combination of offline processing and then online processing. So interesting opportunities there. In general, the Achilles heel of these technologies are scalability and performance issues. There are only so big of models that you can deal with, and sometimes the computation time is sufficiently large that you can't really contemplate doing that at runtime. So looking for ways to speed that up, looking for ways to scale are certainly part of the technical agenda here. Okay, and I've included references here to many of those things. Okay, I think I'm about done, but yes, we have questions.
So one of the things that can happen, right, when you go from open loop to closed loop is you can get oscillations. You
Yeah,
can get
right.
resonances.
That's right.
Have you looked at any of that sort of thing?
Right. So obviously, once you invoke the word control, there's a whole heritage of interesting properties. So, right, stability is certainly one. Settling time, overshoot, and so on. We've looked a bit at those. The context in which this happens tends not to be so easily defined by nice, clean differential equations. So the reasoning is a bit more complex. But generally speaking, the way we deal with that is to look at different horizons over which this works and to try to picture out how the sequence of repairs will work. We haven't done a lot with that. It's certainly an interesting question. And I think right now, if I look at the community of people in the software engineering world, they're starting to talk a whole lot more to the control systems people. So I'm expecting we'll learn more and others will learn more with that kind of engagement.
I think it's one of the issues here, especially when you deal with the momentality events, is the partial observability.
When you deal with what?
Partial observability.
Yes.
So stochastic game is not partially observable. Means the state of the system may not be fully deterministic at the time.
Absolutely.
So, and Prism does not support this script.
And what?
Prism. You're using Prism, right?
Right.
Does not support this script. So you assume you have a snapshot of the system, maybe, and everything's kind of well deterministic at any point of time in order to make strategy generation and tactics generation easy.
Right. Well, so one of the things we're starting to do is explicitly represent the uncertainty of the model variables that we've got and reason about the extent to which the uncertainty region could put us in a high-risk situation of doing the wrong thing. One can go to much more refined models or elaborate models, POM-DPs and so on, which will put us outside the Prism world and are orders of magnitude more complex in terms of computation. I'd rather not bite that bullet right away. I'd like to see how we can sort of inch up on reasoning about that kind of model uncertainty, perhaps in a slightly more specialized way, but still computationally tractable. So it's an important point, and it's certainly one we're aware of. Yeah.
Can't you take POM-DPs and at least approximately represent them as blue state MDPs and then put it back in the Prism capable world? I mean, it's going to be like a scale problem, right? So you're going to have to sort of dial how finely you quantize stuff, right? But it's not like outside of the technology to deal with some level of partial observability within the same framework.
I think it's
Possible, but not terribly practical.
yes.
No.
That's the way you might say it.
I mean,
Academically possible, but not.
The question is how many states you have, right?
Of course. And for anything real, you're going to have huge numbers of states. And I don't know if you're using simulation or you're using the Markov solvers.
Both.
Maybe the multi-agent approach might be.
Does that give you more than games?
I mean, it just gives you more controllability because you don't have to solve the whole thing in one place.
Right. So that's another issue I didn't have on my list of work, but other things we're doing. I think in practice you often find that you don't have a single system that's adaptive. You have a set of systems, and each of them has a certain set of local goals that they're trying to achieve, which in aggregate may or may not give you a global desire. And so you need some way to adapt the adaptive systems, and we're starting to look at that also. But that's just very preliminary now.
All right, thanks very much, David.
Okay.